Okay, here we go. We are starting atomic theory, and you can't start atomic theory without talking about electromagnetic radiation. Why? Just a minute and I'll tell you. So, first of all, electromagnetic radiation is a form of energy, and the reason why we're talking about it right now is because it has both wave and particle characteristics. Okay, that is a really big deal because it's very confounding to our physical world to talk about something in both these dimensions. A wave is nothing but energy. A particle is matter. So the weirdness about electromagnetic radiation is it's marrying energy and mass. Okay, now let's take a walk down memory lane. Focus.
And light does that too, right?
Yeah, we'll talk about light is a bit of electromagnetic radiation. So let's talk about the portions of a wave, so we're all talking about the same thing. This is called the midline. The top parts, the highest point from the midline is called the crest. The lowest point from the midline is called a trough. The distance between two equivalent portions of a wave, I don't care where, from crest to crest, trough to cross, trough to trough, midpoint to midpoint, is called a wavelength. Start yourself a little bit, and remember, where it says wavelength, remind yourself it's a unit of distance. A unit of distance. Okay, the amplitude is the distance from the midpoint to a crest. From the midpoint to a crest. Okay, so the wavelength that we give the variable lambda to is the distance between two successive peaks of a wave, or two equivalent portions of a wave. The frequency, this is not a V, ladies and gentlemen. This is a weird little thing. It's called nu. It's not a V. Is the number of wavelengths that passed a given point in a second. So if you were standing out on the dock in Galveston Bay, and you were a stationary object, you would be able to count the number of crests that passed by you in a certain amount of time. That would be the frequency. For us, we are going to be using the period of time as a second, the number of wavelengths that pass a given point in a second. Velocity, which unfortunately has the abbreviation C, for electromagnetic radiation, we're going to take the velocity of this radiation in a vacuum. It always has the same value. That's the speed of light, 3.0 times 10 to the 8th meters per second. 3.8 times 10 to the 8th meters per second. The velocity, which is constant, of electromagnetic radiation is equal to the wavelength times the frequency. Because of the form of this equation, this constancy, you should be able to see from your mega math knowledge that these are inversely proportional to each other. If the wavelength is long, the frequency is short. Okay. All right. Now, electromagnetic spectrum has all the wavelengths of radiation from very short gamma to very long, no, that's not right, yeah. Very short gamma to very long radio waves. And in the center is the visible spectrum. Our eyes only see a very small portion of electromagnetic radiation, just the visible. You recall the visible light is broken up into the very handy Roy G. Biv, yeah? Okay,
This
yes.
electromagnetic radiation is everything from radio waves to gamma waves, right?
Right. Okay. So, we will be watching a video that goes through all of the electromagnetic spectrum in just a moment or two. Okay. By convention, we're going to be measuring wavelength in meters because we want to use the speed of light in meters as well. And the frequency will be measured in hertz. Another way to write hertz is 1/second. All right, you do need to know this. Nobody's going to tell you. This is your own little, I remember this equivalency. 1 meter is equivalent to 1 times 10 to the 9th nanometers. Oops, knocked that. The visible spectrum is generally measured in nanometers. You cannot use nanometers in your equation. It doesn't work out right. Okay, now to the black and white copy. Okay. The brilliant red colors seen in fireworks are due to the emission of light with the wavelengths around 650 nanometers when strontium salts such as strontium nitrate and strontium carbonate are heated. This can be easily demonstrated in the lab by dissolving one of these salts in methanol that contains a little water and igniting the mixture in an evaporating dish. Not in my room, they're not going to be. This is one of the most dangerous things teachers ever attempt to do. Methanol is highly, highly, highly flammable. And I think the last time I heard, the last settlement against a teacher was $1 million.
Jeez.
I don't have $1 million.
Yes.
So we won't be doing this in my
That's only
class.
2 months' pay, isn't it?
Yes, it is. Thank you. 2 months pay. Can't do that. All right, very, very dangerous. So we watch the YouTube video instead. Let somebody else take on that kind of liability. Calculate the frequency of red light that has a wavelength of 6.5 times 10 to the second nanometers. Calculate the frequency of red light. Well, so far the only equation we know is the speed of light is equal to the wavelength times the frequency. We know the speed of light is a constant 3.00 times 10 to the 8th meters per second. We do know the wavelength, and that is 6.50 times 10 to the second nanometers. We cannot mismatch our units. Fortunately for us, we know that 1 meter is equivalent to 1 times 10 to the 9th nanometers, which means that this term is equivalent to 6.5 times 10 to the negative 7th meters. Here's a clue for you. Visible light, measured in nanometers, always has the exponent -7 when you change it into meters. All right, so we would like to know what the frequency is. If you manipulate this equation, anytime you want to know either one of these, it very nicely has the speed of light on top. In this case, we would like to know the frequency, which is equal to the speed of light over the wavelength. That is equal to 3.00 times 10 to the 8th divided by 6.5 times 10 to the negative 7. That is equal to 4.61 times 10 to the 14th hertz. A hertz is 1/second. Okay, this is the frequency. Now I want you to think about what that means for a moment. Would you be able to see these waves passing by you? Absolutely not. That is a lot of waves passing by in 1 second, correct? Lots and lots. So if the frequency is very high, what can you say about the length of the wave? It's very short, as evidenced by this teensy number. Okay. Let's now talk about the most overused word in science, quantum. A quantum means nothing more than a package of. You can have a quantum of eggs, and you would be talking about 12. You could have a quantum of tires. A quantum of Skittles, if it's in the bag, that would always be 16. Why do I know that a small bag has 16?
Did you count them again?
I did count them. Okay. A quantum of light energy is also known as a photon. It turns out that you can't let out light a little bit at a time. You can only let it out in chunks. Those chunks are called photons. Those chunks have discrete energy to them. Do you understand what I mean? Okay, how many people have
Photon is part of light, right?
how many people have seen a ramp, like going up the handicapped access? Okay, when you have that ramp, you can be in any one of those places at any time, correct? Okay, and they use those because it's easier than going up the stairs. You can only be in these places on the stairs. Do you understand? So this would be quantitized, meaning that it has a discrete amount of potential energy as you're going up. While this is not quantitized, you may have infinite number of potential energies depending on where you are in the ramp. Okay. So this really, really smart guy named Mr. Planck, I can't remember, I think his first name, maybe Ernst, demonstrated that, okay, now,
Wait, so the ramp is quantized in the...
no, the other way around,
What?
the other way around.
So the ramp is discrete.
No, the ramp has infinite numbers of potential energy. The stairs have finite or quantitized amounts of potential energy depending on.
Was discrete.
Discrete means, this would be discrete. Good? All right. Now, all of a sudden, I've made this jump from light to an atom. Where and why did I quit talking about light and now talk about atoms?
That's the wave and particle.
The electrons behave as if they are a wave and a particle. So it turns out that some of the knowledge that was gained by people talking about electromagnetic radiation is applicable to an atom when we're talking about energy. And when we're talking about the atoms, we're talking about the electrons in particular. So Mr. Planck noticed that when energy is gained or lost by atoms, it always comes in packages with multiples of some number, which was kind of really a cool observation for him. And we've decided that the energy lost or gained by an electron is equal to Planck's constant, a number that was mathematically derived by him. Check out this number. Okay, you know what? I just stop it at 6.626 times 10 to the number negative 34. And the only reason why I remember 626 was I had a telephone number that started with 626 once. So there we go, just this big. 6.626. My telephone number? I believe it was in Michigan somewhere.
So that's...
Times 10 to the negative 34 joules energy.
You lived in Michigan too?
Times 8, 4 times.
What?
Maybe 3
Where
times.
have you lived?
I have never lived in Washington.
Have you ever lived in Alaska?
No, I haven't even been there.
This,
Colorado.
Been there, lived there.
So H is that constant,
New
and
Hampshire.
what is N?
Arizona.
Hang on, been there. Okay, can I please go back to the planks?
Yeah.
All right, I will tell you that I have had 26 different addresses. 26.
Gonna move on us?
Good, I'm thinking about it. Been in one place way too long. Okay, here we go. The changes in energy is equal to Planck's constant times the frequency, and then this integer. What that integer is corresponding to what place on the stair. Get it? This would be 1, 2, 3, 4. Okay, now we get this. All right. So all energy gained or lost by atoms, what part of the atom? The electron is a whole number multiple of Planck's constant, H, and frequency. Hence the stepwise or quantum nature of energy change. The blue color in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees C. Then the compound emits a blue light having a wavelength of 450 nanometers. What is the increment of energy, otherwise known as the quantum of energy, that is emitted at 4.5 times 10 to the second nanometers by copper 2 chloride? So we best get a plan here. What would they like to know? The energy. What do we know? The wavelength. Name a way to solve this. I need an equation. Use the first one?
I think we could use the second one.
I think we could use the second one too. I think this is what I need. Most of the time, in fact all of the time, the integer is left off because now you realize that it has to be a stepwise amount of energy. The n was just to show you that it was going in steps. Now that you've realized that, we can drop the integer from it, okay? So, the only other thing we know is Planck's constant. This isn't working for us, is it? I want to know this. I know this. I need to know this. How can I find this? How? The first equation. So, I need to solve for this. I need to, this is nanometers, my bad. I need to make this into meters, which would be 4 point. Okay, now I'm ready to go. Pretend that looks like a lambda instead of a mushroom. I have to consult my notes since I do not have a calculator. Oh, I got it. Anybody else? 6.67 times 10 to the 14th. Okay. Do you know how to do this? How to resolve these units?
The multiple.
Yeah, you flip, so you would multiply. So if you multiplied something like this, oops, you flip and multiply. You would end up with just 1 over seconds. So the unit for this is 1 over seconds. What?
Did we get that 4.5 times 10? Oh wait, that's
In meters.
meters.
Okay, so now I believe I know this and this, and I'm ready to go. You know what? You should just kiss your calculator right now. Right now. Yeah, say, I love you, my little calculator. Because back in the day, you would be doing some math. Now you're just clickety-clacking it. Okay, and the answer is 4.41 times 10 to the negative 18th joules. Do you see why why it's just joules? These cancel.
It's negative 19.
Negative 19? Oh, yeah, it is. Okay. Can you do those on your own? Sure. Okay, then time passed, and a lot of folks were doing a lot of things. This was the pivotal years in science. This is about 1905, and that's when a lot of really smart guys started doing stuff. Most notably, Mr. Einstein. Alberto, although I don't think he liked being called that. Not quite sure. All right, well, one of the leading scientists of the day was Mr. de Broglie, and he took the duality that was driving everybody crazy. What was the duality? What? Yes, that whole thing about being matter and energy together. And he combined them in this fabulous equation. The wavelength is equal to Planck's constant. Okay, can we do this later? I'll be glad to help you out. The wavelength is equal to Planck's constant over the mass in kilograms times the velocity. The mass in kilograms times the velocity. Okay, and I did something really bad to you. I'm so sorry. This should be an equal sign. Okay. It has a negative sign in there, and I just had a typo. This is a negative sign. Planck's constant equals this number. All right, now in order for me not to drive you crazy with deriving units, you must remember to use the mass in kilograms and the velocity in meters per second. Are you willing to do that? Yes? Otherwise, I'll do that long thing, you won't get it, and we'll just confuse ourselves when indeed we want to see how fabulous this equation is. Now, here's another tidbit of information. Everything has a wavelength. You have a wavelength. I have a wavelength. It's not really germane. Do you know that vocab word? It's not really applicable to big things like us. It doesn't really make a hootie patootie. But for really teeny tiny things, that wavelength matters. So right this moment.
Are we like vibrating or something?
Yes, you're oscillating more correctly. Yes, you are. We all are oscillating. Okay. Compare the wavelength for an electron that has a mass of 9.11 times 10 to the negative 31 kilograms, traveling at a speed of just under, well, an order of magnitude under the speed of light, with that for a ball, 0.10 kilograms, traveling at 35 meters per second. I suppose that's possible. I would have to do some math to see. So let's start with the electron first. All right, the wavelength is equal to Planck's constant over the mass in kilograms times the frequency. Okay. What do we know here? We know this, we know this, and we know this. Are we good to go? Okay, so Planck's constant, 6.626. Oops, look, 626 times 10 to the 34.
Is that a B or a new up there?
This is a B. Over the mass, which is itsy bitsy, times the speed, which is large. Do some math, and the wavelength of the electron okay, so that means the points between here and here is, let's see, I need 727, so put 10 zeros. That's not a great distance, is it? Okay, if it's not a great distance, what about the frequency?
Frequency's gonna be very high.
Frequency's going to be very high. Okay. Now let's look at the ball. And the ball has a wavelength that's equal to Planck's constant over its mass times its velocity. And the ball has a wavelength all right, this is an incredibly, incredibly short distance, is it not?
Yes.
Yes, absolutely infinitesimal. The number of these waves that are passing by you in 1 second is a lot, a huge number passing by.
It's like,
I don't think we can even describe.
It's 4 times smaller than now.
Okay, now, remember I talked about that white light stuff? Okay. It turns out we need to go back to light again in order to talk about the electrons. Okay, a continuous spectrum, like the light that's coming out of any light source like the sun, these would be a white light source. If you pass it through a prism, something that's able to bend light a little bit, it will make a rainbow pattern, which is the entire visible spectrum, Roy G. Biv. Okay. The reason why we're talking about the way that white light acts, and now we're going to go back to the atom, because it turns out that when electrons move from one place to another, when they fall down in energy level, they will emit a color of light that is very characteristic. What can I do for you?
Would you like to buy a pumpkin bar or maybe have a cup and get these
Oh, thank you, but no, because you know what? People have been feeding me pumpkin bars for about 4 days, but boy, are they good. Bye. Sorry, Izzy has one. Okay, so this, like we were talking about the fireworks before. Strontium is red, that copper is blue. That's all because of the electrons being excited by energy and then falling back down. Okay, so pay attention here. When an electron in an atom is excited, the electrons absorb energy and they're promoted to a higher energy level. When they're at a higher energy level, they are unstable. And they generally go back to their ground state. Ground state means a place lower than the excited state, where they are very stable. When they move down an energy level, they emit a photon of light in a certain wavelength. The pattern of the wavelengths is called the line spectra, and it's unique to each element. How do they know the elements on Uranus?
It's Saubinger.
They figured.
color?
Educated guess.
They dropped the roof on it.
Color. They they looked at the line spectra of the gases being emitted by Uranus, and they decided what it's made of. Because it's like a fingerprint for an atom. Every single atom has its own line spectra. How many people remember the tubes that I would put up at the front, and you got to wear the kitty cartoon glasses?
Oh, I love that.
Yeah, that was fun, wasn't it? Okay, it turns out what you were watching was the line spectra of each one of the atoms. Okay, so the takeaway lesson for this is, you are so lucky you don't have to memorize all of this. There are a series of energy levels. The ground state, the lowest energy level, is n equals 1. If you add a certain amount of energy to an atom, it will raise it up to a higher level. Depending on the amount of energy you put in, depends on what level it goes to. Let's say you put in enough energy to put it to n equals 4. When it's hanging around in n equals 4, it is really unstable. It can't stay there. It comes down, and as it comes down, it gives off a packet of light known as a photon, which is characteristic.
Are there colors on that chart being full, or are they just colors?
They're just colors. They're just colors. Okay, now in Chem 1, you just put on the funny glasses and we're like, woo, that's great, let's do this again. In Chem 2, you have to tell me the energy change when this happens. Oh,
We get to see the colors.
maybe.